And now in this video, we'll move into our last little section of the class. We'll start with section 11.8 and discuss power series, but these last three sections, 11.8, 11.9, and 11.10, they all go together to kind of serve as our final unit. Now, just thinking about what we've done to get to this point. For a lot of people, chapter 11 up until now, it just really doesn't feel like calculus that you've seen up to this point. That for most of calculus, people are more accustomed to thinking about functions and looking at derivatives and antiderivatives. Well, just to point out that we certainly have taken lots of limits, and limits are actually one of the more basic, more integral parts of calculus. So we have seen lots of limits, and all the sequences and series notation, they have a lot of other purposes in mathematics and other areas of science, of computer science. So they have a lot of other purpose, so they're all good things to know. And of course, ultimately, everything we've done has been a real challenge in using logic correctly and just really applying good analytical reasoning and thinking skills. What tests might work, being able to go through and use a test and make good conclusions. So everything through 11.1 through 11.7, our previous test material, all that has a lot of purpose and serves a lot of good reason for whatever your major is, for whatever purpose you're here. But this is ultimately what we've been working towards. We needed to discuss sequences to then understand and be able to expand on that and talk about series. And now we've been working with regular ordinary series to get to this point and work with what we call power series. Because one of the first things I want to start with, the book jumps right into what is a power series, but I just want to take an extra couple of minutes. I want to start off by presenting a function. Summation. Let's look at this particular function. This is the function f of x. It's got its function notation, but then we're looking at a series. If we expand that series, start plugging in, here I started with n equals 1. In just a moment, this will be the point when we start our series at n equals 0 instead of n equals 1, and I'll show that in just a few moments. But just right now, if I just started expanding this, we'll plug in 1, I would get x over 5 to the first power. Then plug in 2, I'd get x over 5 squared, x over 5 cubed, and that would just continue going. You can note this is a geometric series, moving from one term to the other. I just keep multiplying by x over 5 so that our ratio, our common ratio for this geometric series would be x over 5. But the point is, we've been used to using n as our counting variable, but we've always had numbers inside of here. So something like minus 2/5 to the n or minus 3 to the n over 5, all things of that nature. We've had numbers. We use n as our counting variable, but then the terms themselves are numbers. But now we have the extra variable x in here, so our sequence terms still contain that variable x. So how do we treat this as a function? Well, the same way we always did. If you want to know what is f of 1, well, in your function notation here, you replace the x value with 1, so you do that over here. Now I'll do it in the generic notation, not in the actual expanded terms. When I do that, I would get this expression. But right now, you're not done. The equivalent right here, let me use a secondary function, and let's keep this simple. We'll let g of x be x cubed minus 5x plus 4. And if I ask you, what is g of negative 1? Well, literally, just like I did here with positive 1, I replaced the x here on the notation, so I did that on the other side as well. So the equivalent here, I'd get minus 1 quantity cubed minus 5 times minus 1 plus 4. But is that enough? No. In regular functions like this, we wouldn't stop. We'd keep going. So, okay, the whole point of functions, you input a value x to output some value y. Well, here, what is the y? Well, you go through, do the arithmetic. You get minus 1 plus 5 plus 4, so you would end up getting positive 8. So g of -1 equals 8. We plugged in that x coordinate, but then we did the work to then get the appropriate y. Now, in different contexts and different settings, in a regular function, the input the x, the output is the y. If this was the derivative function, we'd input an x, the output, the y in the derivative, would be the slope of the tangent line to the original function. If you go back, you should have a little experience in Calc 1. You could define a function as a definite integral. You've seen functions like this. Just keep this simple. So now if you input a value x, the output would be the value of this definite integral, which would then really be interpreted as the area under this curve from 1 to whatever that x is. So something like h of 2 would be the area under this curve from x is 1 to 2. So the actual understanding of what that output is and what it represents, that can vary a lot, but in every one of these circumstances. Here, you don't just plug in the -1, you do the work to get the output. Here, if I wanted h of 2, I wouldn't stop here. I'd have to keep going. I'd have to solve this integral, which means take the antiderivative, plug in the bounds, do all the work, and when you're finally done, that would be your output. So now I say all that to come back up here. What's the output here? All I've done so far, I've replaced the x with a 1 here, replaced the x with a 1 here. That's this equivalent, this stage, or this stage, but I still have to do the work. Do the arithmetic, solve the integral. Here, what's the work? Find the sum of this series. Now, this is where, how would we know the sum? I mean, we just spent so many lessons in the earlier part of chapter 11 just establishing, does the series converge or diverge? We only had a couple of series that we could know what they actually converge to. But luckily here, this is a geometric series. So I know it will converge because now I know specifically, generically, r was x over 5. But now that I've plugged in, now I specifically know r is 1/5 and the absolute value of r is less than 1. So I know this converges. What does it converge to? Well, here's a reminder. Remember, this is just for geometric series here. But if we know we're looking at a geometric series, a, the first term, divided by 1 minus r, that common ratio. Well, your first term here, remember this wasn't that perfect form a r to the n minus 1. So how do you know what the first term is? You plug in the first value for n. And, I mean, either here I did it generically and now plug in x is 1, or now do it specifically now that you've already plugged in x is 1. But the first term here would be 1/5 over 1 minus r, which again, r, just a coincidence here. That doesn't always happen. We've seen examples where that certainly doesn't work. But now finishing this, so 1/5 divided by 4/5, that becomes times 5/4. So now that's the work. F of 1 would equal 4. We input a value x, even though it seems strange as a function written as a series, but we could still plug in that x, do our work to figure out what that actually adds to, and that final sum, the convergence value of this series, is the y value for this exact function. So that's just getting us back to functions. From kind of this point on, I still want to take one more moment and just show you just a tiny bit more here before we get into the more common aspects of what is a power series, what is it that you need to be able to do in this section. So we're getting to all of that. But this, again, is giving you the big picture. That power series, that we can have functions written as series, where we still have an x as a part of the individual terms inside of that series. This introduces a whole huge branch of functions. And as we keep moving along in 11.9 and 11.10, we'll see ways to take regular functions that we deal with all the time and be able to find the corresponding series, power series function that would go with it. That's going to be one direction that we go. But on top of that, now that's a function. So as a function, well, x's and y's, basic inputs and outputs. But now we should also talk about derivatives and antiderivatives. And that's what we're going to get to. The derivatives, antiderivatives, that's actually a lot easier than you think. So we'll save that. That really comes up in 11.9, but we are going in that direction. So the last thing I want to do right here is talk about the domain, right? If we think about basic functions, any type of function we're thinking about, and again, we're more accustomed to our basic functions, just, a function written as an equation. And when we think about domain of those functions, it's all about what works. What x's can you plug in so that you have a legitimate y value to go with it? Well, this particular function, you can plug in absolutely any x you want. The domain of function g would be all real numbers, negative infinity through positive infinity. If this had more to it, I don't want to change the function because we've already done some work with it, but pretend this had a denominator divided by x squared minus 9, well, you can't have 0 in the denominator. So we'd see what makes the denominator 0, x squared minus 9 equals 0. We'd see x equals positive and negative 3 are the discontinuities, and the function is continuous, and not even so continuous here, more so just the domain. The domain is everything except those two values. X cannot be plus or minus 3, but could be anything else. We've also seen situations if we had a square root, you can't have negatives under a square root. So just the reminder here, the domain is about finding what x's make things good. What x's can you plug in that you get an output that makes sense? We'll come back up here for a moment. I had you plug in x as 1, and I did show you on the side, this is a convergent series. That's why I was able to do this work and find what it converges to. But what if I asked you to find what is f of negative 7? Well, it still seems easy. You'd plug it in, you'd get the series negative 7 over 5 to the n power. And if you go too quickly through that, people have the bad habit of just, it's still geometric, go right to this formula. But remember, it's only if the series converges do you get to use this formula. This does not converge. Here, the absolute value of r, you'd have r is negative 7/5, so the absolute value is positive 7/5. That is greater than 1, so this series diverges. If this series diverges, you don't get a nice sum. Now, it doesn't matter why this diverges. Does it diverge because it's going to infinity, negative infinity? It just oscillates and bounces all over the place. It doesn't matter what case this happens to fall into. The fact that this diverges, we can't get a nice sum. Therefore, minus 7 is not an element of the domain. This is not a nice x value that gives us a nice y. This is what we're really going to focus on a lot in 11.8. We're going to start looking at what are the x's. We're slightly changing the question now. We're not going to look at this series and ask, does it converge or diverge? We're not going to ask that question. Oh, sorry, right here. So we've got a same series I had written at the top. I don't need the f of x notation anymore, everybody. This is where we're starting to really make that jump into the actual content of 11.8. Because we're starting to show you our first real question. It's not even really the first, it's the big question. There's just a few little tweaks that we'll see on this question, and that's what 11.8 is going to focus on. So again, I'm not going to say, does this converge or diverge? The question is going to be, what values of x does the series converge? And what I'm going to show you in just a moment, the answer is always at least something. You'll never get a series, a power series like this with variable x, where the series completely diverges. There will be some x's. Now, general. There will be some that always converge no matter what x is. But at a minimum, there will be some x's that converge, and there may be some x's that diverge. So again, that's why we're changing this question, and we're going to this question. And I'm still going to this as our first problem, because even without me giving you any other tools and still having more I want to explain before we do more problems after this first one still works out so nicely in so many ways because we already know it's a geometric series. Right back to the top here, though, is the first thing I identified when I started writing out the terms. This was a geometric series, and without plugging anything in for x, this is the generic value for r. Well, go to both of these. Once I did plug in specific values for x, then I looked individually. Well, now this is r, this does work, so this one does converge. But with this r, this does not work, so for this value of x, it diverges. Let's do this generically. Let's go back to this r value in this generic series and realize, okay, as long as the absolute value of r is less than 1, then the series converges. Well, let's take the absolute value of r. Generically, r is x over 5, so absolute value of x over 5. And let's solve this inequality. Let absolute value x over 5 is less than 1. Okay, how do we solve this? Few quick reminders. You do have an inequality here. We do not have n. Remember, all those inequalities and absolute values, when we were dealing with plain old n, we didn't have to worry about negatives and multiplying and flipping the sign from less than to greater than. Here, well, there's a couple of good things, but the first thing is first the x over 5. Having multiplication or division, you can take absolute value of top and bottom or first and second, as long as it's just multiplication, division, not addition, subtraction. So this becomes absolute value of x just over a plain 5. Now I can think of cross multiplying. Some people treat this like it's 1 over 1. Other people just multiply both sides by 5, trying to isolate the absolute value. Either way, we get to the same line. And now realize there are a few little things, hopefully you remember, about dealing with absolute value and inequalities. But an absolute value becomes two inequalities. If it's a greater, this is just a quick reminder, if it's the absolute value of x is greater than 5, we get two possibilities. Either x is greater than 5 or x is less than negative 5. Those would be the two inequalities that come off of this one. But for our purposes, you'll see we are always going to use a less than, so that's not really going to be helpful for us. And the less than becomes a little cleaner. Instead of having two separate inequalities, we could write this all as one. For the absolute value of x to be less than 5, x has to be sandwiched between the values negative 5 and positive 5. Again, language, if you write this as two inequalities, this has to be an and statement, not an or. X is greater than negative 5 and x is less than positive 5, but it's so much easier to write that just like this. This one, now we're done. If there was a little bit more trapped inside this absolute value, if it was something like absolute value 2x minus 1 is less than 5, well, now we'd have 2x minus 1 is between these two. We'd subtract 1. Now it's not even left side, right side. It's just all sides. If we had 2x minus 1 in here, you'd add 1 to all sides. You divide 2 by all sides. Now we would have to worry about if that was a negative 2, you'd have to flip your signs. But again, this one worked out very nicely. So this series converges for these values. In the language of functions, the domain of f would be negative 5 to 5. And in just a moment, This idea of for what values of x does the series converge, we are going to formally call that the interval of convergence. I will define that in just a moment, but that is exactly what this is describing. I mean, actually, I'll just say it right here. An interval of convergence, by definition, is the values of x that make the series converge. That is a verbatim definition of this term. Just for short, I sometimes abbreviate it I of C, interval of convergence. I certainly give you permission to write that as well. So giving you this series, saying for what values of x does the series converge, writing it as a function like this, and saying what is the domain of this function, or again, going back to the series and saying find the interval of convergence. All three questions are asking the exact same thing and would be done and solved in the exact same way. So, I mean, I guess the only last thing would just be how you write your answer. If you ask the domain, you could write domain notation like this. If you're asked the I of C, the interval of convergence, same answer, and you could write it in the exact same way. If they just said for what values of x does the series converge, well, then you don't have these formal terms, but you still would have this interval as your answer. So no matter what way you look at it, our answer is -5 to 5. Okay, so we have said and introduced a lot so far. But now let's keep going. Let's get a little more formal here. I've mentioned power series several times, but now let's actually formally introduce what is a power series. Our book does this in two parts. They start off with a generic power series is written c sub n x to the n power. But now this is where we make a little switch. We now start at n equals 0 instead of n equals 1. And even at this exact stage, that's not so clear to so many people why we do that switch. It's as we get a little further. It's just a little bit for notation. Honestly, a lot of it has to do with the geometric series. The geometric series, we initially had n equals 1, and we had ar to the n minus 1 power. Well, if you start at n equals 0, that just makes that work a little quicker and makes your exponent a little cleaner. When you use n equals 1 and start with n minus 1, you still get that term to the 0 power. So why not just start with n equals 0 and make that first exponent 0? So that's a little bit of a rationale why they do it. There's a few other reasons, but it's just a little simple point to realize we're now starting n equals 0. So if I expand this, I would get c sub 0 x to the 0 power plus c sub 1 x to the first power, c squared x squared, c sub 3 x cubed plus ... and this continues forever. It's still an infinite series. But as we saw on the first page, now we've got variable x mixed in our terms. I mean, in little things, x to the 0, well, as long as x is not 0, anything to the 0 power is 1. So we make that assumption. Let's assume x is not 0, so we could just go c sub 0 plus c1x to the first power, and I don't need to write to the first power, and then the others follow as they were. But the point is that now in our power series, it's like we have two things going on. We have the power of x, whether, again, this first one, technically the power of x is not there if you really break it down to the 0 power. But then we keep getting this increasing power of x, x to the first, x squared, x cubed, x to the fourth, and so on. But then we also have these extra coefficients, and that's why they're using a c. It's the coefficient, and this subscript is just making it clear c sub 3 is the coefficient that goes in front of the x cubed term. C sub 2 is the coefficient in front of the x squared term, and so on. So that's part of the notation here. If we started with n equals 1, when you get to the first power, you'd have c sub 2, so that wouldn't match up as well. But these coefficients can be anything. They are often their own sequence on their own. So some people look at it like this power series has a sequence of coefficients and it's all attached to a sequence of variable x. So that's the original power series that they start with. But I need to point out, it's not always just a plain x. So this is the better notation for a power series centered at x equals a. Okay? And that's the same notation. Our book uses a for this as well. It's the same idea, just instead of having x to the n power, it's x minus a to the n power. So now if you expand this, you'd still get c sub 0. X minus a to the 0, we're still thinking of that as 1. C sub 1 times x minus a to the first power. C sub 2, x minus a squared. C sub 3, x minus a cubed. And again, plus dot, dot, dot. That still continues forever. What's the big deal about the center? The center is the value for x that when you plug in makes everything 0. Plug in 0 for x here, and it doesn't matter what the c's are. Anything times 0 is 0. So if you plug in x as 0 here, you're essentially just adding 0 forever, and you get 0. But now, in the more general term, you plug in 0 for x, you get 0 minus a to a power. Well, how does this whole thing go to 0? It doesn't go to 0 when x equals 0. It goes to 0 when x equals a. So if you plug in, let's go back to the first one. Plug in 0 for x here. You could still expand it, but it's all just a bunch of zeros. Okay? But now, if I look at if this was x minus 2 to a power, now x equals 2 would make everything 0. So that's the first point we want to make about our center. And now, before we wrap all this up, we have a lot of examples we want to do to get good practice, but let's point out the reality of power series. Like I said a moment ago, the question is no longer does the series converge or diverge. The question is, what are the x's that the series converges? Find the interval of convergence. And there's a theorem in our book. The theorem is on page 789, and then there's a nice box at the bottom that kind of spells all this out again and gives you quick examples of each of these cases. But in general, if we have, again, a power series centered at A, here's our theorem. We're starting off with, again, the power series centered at A, then there are 3 possibilities. Regarding convergence. Possibility number 1. We have the series only converges at x equal a. That is the minimum. What I kept pointing out in both of these, whether this one, technically this is centered at 0. Let's make that note, make that clear. If you just have a plain x that does have a center, the center is 0. Plug in 0 for x, everything becomes 0. You add 0 forever, you get 0. You got a final sum. So that would converge. More generically, same thing happens here when x is a. X is a, you're adding 0 plus 0 plus 0 forever. So again, the same thing happens. So that's a minimum. This power series can't completely diverge. If it feels like it completely diverges, well, that's the minimum case. It converges just at its center. Possibility number 2, the series converges for all x. That would literally be, again, there's that upside down a again. That again stands for all. It converges for all x. We would converge here, just one single x value we converge. Here it would converge for every value for x, from negative infinity to positive infinity. by the way, these are the intervals of convergence. That's that box I was talking about. The theorem itself is writing it out just the way I am, but that box at the bottom starts talking about the idea of the interval of convergence. Here, that interval is that singular x value a. Here, that interval is, again, you could call that all real numbers, use that notation, or the interval negative infinity to positive infinity. And number 3, the third possibility, the series converges when the absolute value of x minus a is less than some value r. Here, notice, those are different r's. This is just a capital R. That, in our book, they always write that as that boldface R. I can't do boldface on the notes. That's why we introduced that extra little slash line to make that all real numbers. But that's why some people don't like that notation. They'd rather just use the interval negative infinity to positive infinity, because this letter R is going to come up here. Just as we use I of C, short for the interval of convergence, this capital R stands for the radius of convergence. Now, I'll explain that in just a moment, how that works, where the idea of radius comes from. But here, just pointing this out, that when you do this, you're going to get an interval, and it's going to be an interval centered at A. That's where this idea of radius is going to come up. So just very quickly, let me show you a little work here. If you ended up with x minus 3 is less than 2, absolute value, this will come up in a similar way that we saw with that ratio test. That geometric series is what I meant. The geometric series, that was kind of our example 1. We ended up with absolute value of x over 5 was less than 1. So we ended up right here. The radius of convergence in this one was 5. The center was 0. Notice, this is distance. If you go 5 units away from 0, you would end up negative 5 on the left, positive 5 on the right. So in this problem, the radius of convergence would be 5. And since we're centered at 0, that gave us a nice interval, negative 5 to positive 5. In this one, I want to be clear. I will always focus on the interval of convergence. Several of the problems in our book ask you for both. They say, what is the radius of convergence, and also ask you for the interval of convergence. I want to be clear. I'm really trying to emphasize the interval, but you should understand the radius as well. So in this situation, I already know the center is 3 and the radius is 2. So with that same understanding, centered here, the distance you could go away from here and get convergent values is 2. So 2 units bigger than 3 would be 5. 2 units less than 3 would be 1. That would be your interval of convergence. So that's the literal understanding of how you get this, how you can get to the interval. But if you just solve the inequality, you'll get that. Drop the absolute value, make this string like we said on the previous page. Now solve for x. That's the catch. In the previous one, once we dropped the absolute value, we were done. Here, keep solving for x. Add 3 on both sides, you get 1. Here the 3's cancel, you get x. Here you add the 3, you get 5. Not a surprise, that interval matches this interval. Now back to the theorem. They make an extra point here. The series converges when this happens and diverges when this happens, when the absolute value is greater than r. Notice it doesn't tell us what happens when this distance is equal to r. That's where, at the very end, we'll see. So here's our third possibility. We see just a single point as our interval of convergence. We get all real numbers, or our third possibility is we get an interval like this. These intervals, you typically also have to check the endpoints. That's where some people, when they get to the homework here, they'll do this kind of work, they'll feel good about this answer, but then in the back of the book, they might see like bracket 1, parenthesis 5, or brackets on both, or maybe it's parentheses on both. The last catch, if you're in this third possibility, you often have to check separately what happens when x equals these endpoints. Now, I didn't have to do that here. And the reason I didn't have to do that here is because I specifically knew this was a geometric series. So as a geometric series, I know without a doubt that it only converges when the absolute value is less than 1, and that it diverges not only when the absolute value of r is greater than 1, but also when it equals 1. But in a few moments, you'll see ratio test is really going to be the normal key to solving these problems. We might get lucky with a few geometric series like this one, but most of them, even this one, a ratio test would have worked here. And in the ratio test, we know convergence when L is less than 1, divergence when L is greater than 1, but when L equals 1, we get inconclusive, so we'd have to test the endpoints. So now let's actually go through and do all that. Again, we have said a lot up to this point. Introduced a whole new brand of function, but now we're getting back on track. Now I'm going to give you power series. We're going to start off simply talking about the center, and then we'll move on and talk about the whole convergence, the interval of convergence for the series. So let's start simple. Find the center of the following power series. Number 1, we're going to look at the summation 2 to the n, x to the n plus 1, all over n factorial. Number 2, we're going to look at the summation x plus 4 to the n, all over n squared. Just notice here, I'm going to start this at n equals 1. I know we said we do start at 0, but every once in a while you'll see that change just to make sure we're not dividing by 0. Here, the exponent is actually n plus 1 instead of a plain n. We'll see when we start making our own power series, sometimes things like that will come up. It'll be easier to combine the exponents. Maybe you had an x to the n, but you had an extra times x, so you combine the exponent. So that's fine. And number 3, we'll look at the power series. We'll go 2x minus 6 to the n all over 4 to the n, n plus 1. But in all of these, the center is a very simple problem. Some people like to write out terms. Other people are so obsessed about writing it in this form. But as we explained, it's all about what makes the x term go to 0. So I'll come back and rewrite all of these in that exact proper form, but what makes x 0? 0. That's it. If x is 0, there's no extra addition, subtraction. 0 to a power, 0 times 2 to a power, 0 divided by a factorial, that all just equals 0. The center is 0. Here, x plus 4 to a power. Well, now x has to equal negative 4. That's it. Negative 4 plus 4 would make this 0. And then everything I just said here. Once this piece is 0, raise it to a power, divide by anything squared that you want, but that is giving you a 0. Okay? Last but not least, now x would be 3. So again, like I was saying, little things. Some people, they just always find the x term, whatever x, whether it's attached to something by addition, has a little multiplication and subtraction, but whatever that x term, wherever it's located, take that entire piece and set it equal to 0. So here, x equals 0, and you're done. Here I'd be setting x plus 4 equal to 0, and that gives me the negative 4. Here I'd be setting 2x minus 6 equal to 0, and that would end up giving me x equals 3. The last thing some people do, and I think this is probably the least desirable option, again, they obsess. They need to see x minus a to a power. Well, how do you write x as x minus a to a power? You write it as x minus 0 to that power. That confirms. Some people also here, instead of writing x equals, they write a equals. They're kind of already holding that value a as the center value. But notice that a is still an x coordinate. So whether you call it a equals 0, a equals negative 4, or x equals, it's the same thing. It's, it's a little bit like critical values back in Calc 1. Some people, because they're critical values at the end, they like to call them c, but they're really just x coordinates. Okay, so solve that inequality. Or now thinking of it as x minus a, well, how do you write x plus 4 as x minus a? You got to make that plus a minus a minus. X minus, and there is your corresponding a. Okay, how about this one? Well, again, setting it equal to 0, not hard. We get x is 3. But you could also play games here. You could factor out a 2 and be left with x minus 3. All of this is to the n power. So now that it's attached by multiplication, I can distribute that exponent n. So that 2 to the n, we can keep going now. That 2 to the n could combine with this 4 to the n and become 1/2 to the n power. There's more we could connect and simplify here. But just for the point of finding the center, there's your x minus a. We didn't even need an extra negative sign. It's perfect. X minus a equals 3. All right. And now we get to the good part. It's not good. All of this is good. And by the way, now I'm going to do interval of convergence. If you really want, you can go back and do the interval of convergence for all 3 of these. There's no problem in doing that for extra practice. But now I'm going to move, and here's the big question. Let's find the interval of convergence for the following power series. So again, that reminder, I of c. We're not going to be done with that language after we move past this section. So just for short, I of c for interval of convergence. And again, I want to do several examples. I definitely want you to see at least one of every case that we discussed. But examples 1, 2, and 3 in your book do the exact same thing. So again, we've got a lot of little things that we've got going on here. Make sure you're getting good practice. And even though we've discussed a lot of ideas, like I kept suggesting, this is the big picture. I am giving you a power series, and I'm asking you to determine convergence. Not saying does it converge, diverge, saying find the interval of convergence, find what x's it does converge for. That's the big picture. And if your answer is it diverges, something's wrong. Remember, that is not a possibility according to this theorem. It always converges somewhere. It's just a matter of, does it just converge at its center? Does it converge for some radius away from its center? Or does it converge everywhere? Oh, by the way, this idea of radius, the book expands it. This is where the radius makes the most sense. It makes perfect sense thinking about distance. Having some point in the middle and going that distance r in either direction and having every x in between be a convergent value. Well, you could stretch that here. Here in this first one, if you're only converging at a single value, technically your radius of convergence is 0. You go to your center, you go 0 units left or right, and that's all you've got. You've still just got this value. Here, you go to your center, and you could go infinity left or right and end up with this interval. So this stretches the idea of distance because infinity is not a number, it's a concept. But that's how we make these two go hand in hand. That knowing the interval of convergence also can kind of correspond with its radius. Okay, so let's take a look. Let's take a look at problem number 1. Let's look at the power series. N plus 1 factorial x plus 3 to the n power. Here is our first one. Now, this is a little interesting the first time you do it, because even though, as I keep explaining, our question is slightly different now, not just converge, diverge, looking at what x's make this converge, but even though it's, has that subtle difference, we're still going to take the same approach. What am I going to do to solve this? I'm going to apply some sort of series test. Well, what series test? This one has a factorial. Technically, this is a geometric series component, but this is a factorial. We said that ratio test always works well with factorials. So that's what I'm going to do for this first problem. I'm going to set up the ratio test. The limit, as n goes to infinity, this to the n plus 1, right? This is the a sub n generically. I need the n plus 1 term. So n plus 1 becomes n plus 2 factorial. X plus 3 to the n plus 1 power, all divided by the nth term. This is a little interesting, just in that we normally have fractions, so fractions over fractions, but this one happens to be a simpler example, so this is immediately just a clean fraction. But don't forget, ratio test halves the absolute value, and with a lot of our series, we are able to quickly get rid of that absolute value by just looking, well, hey, these are all just n's, these are always positive. And then like if this x wasn't here, hey, 3 to a power is always positive. The absolute value isn't doing anything. If this was a negative 3 to a power, we'd make it a positive 3. But now that we've got the variable x in here, we have to realize that this expression, it might be positive, it might be negative, it depends on the power of x. So simplifying the absolute value here, there are still a lot of places like these, that absolute value can be broken down and just go away. Technically, I'm applying the absolute value to this, 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 and this. They're all attached by multiplication division. So apply the absolute value to each piece, but here, well, this is always positive. This is always positive. But these two pieces, I have to know about x, but I don't know about x. So that becomes absolute value of x plus 3 to the n plus 1 power. Same thing in the denominator, absolute value x plus 3 to the n. That's the big difference with ratio test here. All the initial stuff, still talking about convergence, even though the question is slightly different, still deciding what test works. This is where we're going to see a lot of factorials, so a lot of ratio test, but not just ratio test. Root test also works pretty well here, okay? So ratio and root test are going to be the most common two that get used. Apply them. Well, keep going. Now, still thinking about things cleaning up. This becomes n plus 2 times n plus 1 factorial. So those can cancel top and bottom. This is absolute value x plus 3 to the n times absolute value x plus 3. The absolute value x plus 3 to the n's cancel. So before I take the limit, we still have everything cleaned up, simplified as best we can. This is the second place where people get a little bothered. Again, at the beginning, all this just takes practice and time, everybody. It's not, if you're able to get through 11.1 through 11.7, you can definitely handle this. You just have to give yourself enough time to get used to these subtle differences. because here we talked about x as a variable, so we had to be careful with the absolute value. But in the terms of this limit, n is the variable. Treat x plus 3 like it's a 5, or it's a 10, or it's a -1. That doesn't matter. N goes to infinity. Infinity plus 2 times some number. This limit goes to infinity. And now in a normal ratio test, we would say, well, infinity is greater than 1, and we would conclude diverges. But we can't make that conclusion. We keep going back and emphasizing there is no conclusion diverges here. There's only these three different possibilities for convergence. So which one is it? When you think you diverge, you're in case number 1. Because that's the one little thing that we were ignoring here. We said just treat this like it's any old number, and something times n plus 2 as n goes to infinity is going to go to infinity. Except for one case. If x equals -3, no surprise, -3 is the center. If x equals -3, this is 0. And before you even take the limit as n goes to infinity, 0 times anything is 0, and 0 is less than 1. Now, almost all of us do this. We don't make that separate breakdown. We just pretend this is some number, take the limit over n, get our answer, but now we just make that connection. In both ratio and root test, if you get something greater than 1, you get diverges. But if you get that as an answer, you're really in case number 1. This series, this power series, only converges at its center. So you could use the set notation and just have the single element in it. You could certainly just write the interval of convergence is just the value x equals -3. I'm perfectly fine with either one. The book tends to use this notation more. But that's what we just saw in this first problem. This first problem put us in the first case. Okay, let's move to problem number 2. Problem number 2, let's look at the series -5 to the n plus 1 times the quantity x minus 1 to the n power all over 2n quantity factorial. Just one little thing. I believe we mentioned this with factorials, but just to be clear, 0 factorial initially seems weird, but 0 factorial by definition equals 1. Right? That's the one thing. If we talk about the definition of a factorial, well, 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. You keep counting down until you get to 1. Well, what about 0 factorial? That's just kind of a by definition. This is kind of similar to why x to the 0 equals 1. It's just something we need to make all the other pieces work well and make sense. Just thinking about it, using all your basic information, that just doesn't make any sense. We just have to memorize it. Just like this. Why is anything to the 0 power 1? Well, it's really because of rules. 4 cubed divided by 4 cubed. Well, we know if we cancel, that should equal 1. But if we use our properties of exponents, we should subtract the exponents to get 4 to the 0 power. Therefore, by default, 4 to the 0 power has to equal 1. So that subtracting exponent rule works the way it should for all the other cases. So again, just a quick little aside. Coming back to the problem now, well, same thing. I look at this. I see this as a geometric component. I see this as a geometric component. I see a factorial. I'm still asking about convergence, specifically what is the interval of convergence. So just a reminder, let's find the interval of convergence. So I need to run the appropriate test. And once again, the factorial wins. We are going to run the ratio test. I'm just going to go just a hair faster this time. And as I always say, I'm not trying to rush you. I'm just trying to point out that with practice, you can go a little bit faster with your work. So literally, you'd have a big absolute value, minus 5 to the n plus 1, this to the n plus 1, 2 quantity n plus 1, quantity factorial, all divided by all of this, all in absolute value. But just like we did with regular ratio test, let's just try and go a little faster. This becomes the n plus 2 power, and absolute value would make that minus 5 a positive 5. Here, the absolute value has to stay, but that would just become the n plus 1 power. Here, that becomes quantity 2n plus 2 factorial, but the absolute value is unnecessary. It's already positive. And then I'm dividing by this term, but now we're back to our more common fractions. So dividing by this means times the reciprocal. And once again, that's already positive, so absolute value stays positive. That absolute value piece would make the negative 5 a positive 5, and that absolute value still needs to be there because we don't know what happens to x. Will this be positive? Will it be negative? Well, it depends on x, and we don't know what x is, so we have to leave the absolute value to cover ourselves. But now it's set up. Before I take the limit, I'm cleaning up. There, factorials, that's a big reason why we use ratio tests. The factorials clean up very nicely. But let's take advantage. In this one, other things clean up as well. 5 to the n times 5 squared, 5 to the n times 5 to the first power, 5 to the n's, and even 1 5 cancels. And right here, absolute value x minus 1 to the n times absolute value x minus 1. Those cancel. So I have a 5 and an absolute value x minus 1 from the numerator. That's all that's left up here. And in the denominator, I've got these two. Again, now as we take the limit, we pretend x is just some number. So 5 times some number divided by 2n plus 2, 2n plus 1 as n goes to infinity. 5 times some number is a number divided by infinity over infinity. This is a k over infinity case. This is going to 0. And 0, it's a ratio test. 0 is less than 1. This would be where we just say, in a typical ratio test, that the series converges. But again, the subtle change in directions, what are the x's that this converges? It doesn't matter what x is. No matter what x is, whether x is the center, 1, or is anything else, this will always equal 0. 0 is always less than 1. Now we are in the second case. This series converges for all x. So the first two examples that we've seen, we get something that looks like it always diverges, but that means it converges in its center. And then we get something that just converges, but that means it converges everywhere. So negative infinity to infinity. And now number 3. Again, we're going to do one more after, but you may guess number 3 will put us in the third case. But let's actually go through and see it. I have to say this, everybody, before I even keep going. After some people get into some good habits with this, some people start overblowing the factorials. They saw problem number 1, factorial in the numerator. They saw number 2, a factorial in the denominator. They think that gives them permission to skip the work we're doing. What we just saw is, again, one example of each case. You have to run the tests. Don't try and rationalize an answer based on a previous problem. Do the work. Don't say it's because the factorial. Do the work and show what happens. I mean, I will admit, a factorial in the numerator, it's going to give us a result like number 1. A factorial in the denominator, it's going to give us this same result as number 2. But to get full credit, you have to be able to show the work, not just try and sort of connect the dots by saying these examples are similar. Be able to apply these tests and make definitive conclusions, just like we did with all the regular series work that we did in 11.2 through 11.7. So now, number 3, let's look at the series. Let's keep this one a little simple. Let's look at x plus 3 to the n all over n times 5 to the n. Again, because of this plane n, I have to start at n equals 1, not 0, because I can't divide by 0. And I'm just pointing that out, everybody. I'm not trying to give you any of those kinds of tricks. You know, we start at n equals 0 when we can, but if that would give you a 0 in the denominator, we're not going to start off a series infinity plus. All the individual terms have to make sense. So all those individual coefficients, they have to actually be numbers. Fractions, radicals, decimals, that doesn't matter, but they do have to actually be numbers. So now what situation are we in? Well, if this n wasn't here, that's a geometric series. So just note, no n in the denominator. This is equivalent to this, and that would be a geometric series. So again, we're pointing out geometric series do come up. That was actually our very first example. And with a geometric series, that's your inequality. So you would solve this. You would have absolute value x plus 3 over 5 less than 1. So absolute value of x plus 3 is less than 5. Minus 5 is less than x plus 3 is less than 5. Subtracting the 3, negative 8 is less than x is less than 2. And again, because this was a geometric series, you would be done. You wouldn't have to worry about what happens when x equals negative 8 or when x equals 2. If you do look at those would be R values that give you 1 or negative 1, and those definitely would diverge. But notice again, keep that note. That was without that n value, that's how we could solve, and there would be our interval. But that n is there. So it's not just geometric series components, it's geometric and p series. This is, again, a good place for a ratio test. A root test is not terrible here. If you did all this to the 1 over n power, you'd get that n to the 1 over n. We showed that in the root test in 11.6 video. You can do it, but most of these, come over here, do a root test. It works out the exact same as this geometric series idea. The nth root of this would give you this, and this would have to be less than 1. The absolute value is still on the the root test as well. So it would be identical to what I'm doing here. Except the root test, you would have to go back and do an extra step because the root test doesn't know what happens when the limit equals 1. So you'd have to go back and plug each of these in and then conclude that they both diverge at these endpoints. But I say all of that to get us back to here. The ratio test is once again friendly, very friendly for this because of those mixed components. Again, we've got the geometric series pieces here and a p series piece here. So let me set up my ratio test. And just like this one up here, take your time. No shame at all doing 2 or 3 steps to get to where I am. But it's also great if we could just go that little bit faster here. So absolute value of this, the n plus 1 term, gives me absolute value x plus 3 to the n plus 1, n plus 1, 5 to the n plus 1. That was the only place that needed the absolute value, and all the n's became n plus 1. Divided by a sub n times the reciprocal. But again, that term still needs the absolute value. Cleaning up, these would cancel with one of these left over. These would cancel with 1 5 left over. and I can't do anything more here. So, fully simplified. We're finally getting something a little different here. In our very first example here, we ended up with n's only in the numerator, got infinity, thought it diverged, but realized no, it still converges at its center. The second problem, n's only in the denominator, well, that was something over infinity, went to 0, that was always less than 1, converged everywhere. But now, this times n, number times n, this times n plus 1, number times n plus 1. Two ways people see this. Some people think of dominant terms, and again, this is a part of the n. So the dominant term at the top is all this, the dominant term at the bottom is 5n, the n's would cancel. So this is what you're left with. Other people, n is the variable for this limit. So these are just coefficients. Kick them out in front. They do the rest of their work on the n over n plus 1. They get the limit here as 1. This pushes along. All of this times 1 still gets us to the same place. This is the third case. We've had, again, you look at the two examples, something that looked like it always diverged, well, it still converges at its center. Something that always is less than 1, well, that always converges. Here is the third case. This converges when all of this is less than 1. Same type of work I have over here. Now I have it set up. X minus a is less than r. The 5 would be your radius of convergence. -3 is the center. You can think about going 5 units away from -3, and you would get this interval. Or you could, again, solve the inequality. But here's the big difference, everybody. I've said it now 3 times, but this is the first time we actually have to do it. In the way we solved this one, it was because it was a geometric series, we didn't worry about the endpoints. But because we used a ratio test or a root test, we have to worry about what happens when all this equals 1. So we're not done here. And it's very quick and easy for a lot of people to just say, there's your interval. But then when they look in the back of the book, I'll spill the beans. I'll tell you right now, the -8 is going to get a bracket on it, and the 2 is not going to get a bracket. So people feel like everything they did is correct here, and you're right, it is. But in this third case, if you did a ratio or a root test, you still have to also go back and individually test each of the 2 endpoints. Not with a geometric series. This is now the 4th time we're saying it, because we know absolute value of r greater than or equal to 1 automatically diverges. But in a ratio or root test, if L equals 1, it's completely inconclusive. So what happens when x equals -8? I'd plug this in here. I would get -5 to the n over n5 to the n. These could be combined and become -1 to the n over n. And now doing a little work, this is not obvious, but that's an alternating series. Specifically, it's the alternating harmonic series, but this will converge. -1 to the n, 1 over n left behind. 1 over n goes to 0. 1 over n is decreasing. So this would converge doing an alternating series test. But if you looked at x equals 2, sorry, I didn't give myself a lot of room here. We'll do another one in just a moment. But if we let x equal 2, this would be +5 to the n over 5 to the n. They'd cancel completely, and you would just be left with 1 over n, which we know is the harmonic series, so that diverges. That's why I got the bracket on -8. When I let x equal -8, I ended up with something that converged, but when I let x equals 2, I ended up with something that diverged. And there's no better way, everybody. There's no, well, in this case or that case, you gotta test. Sometimes they both fail, they both diverge. Sometimes they both converge. Sometimes, like this one converge, one diverge. Every one of that third situation, we have to treat it like a unique problem and just see what happens. Okay, so again, there's a lot here, everybody. These are good examples that should really guide you to make sure you feel comfortable, get good practice. Again, you want more examples, examples 1, 2, and 3, so similar to the ones that we just did here. So plenty of good practice for you to go back, make sure you feel comfortable, and I want to do one more before we end this video. Again, 11.9, we'll talk more about how we get these power series. We'll start looking at functions, regular functions, regular function notation, and start see through the regular notation and sometimes through the use of derivatives, antiderivatives, there's a lot of very clever ways to go back and forth between power series functions and our regular series. But like I said, for this video, let's just do one more. Let's look at the series 2 to the n plus 1, parentheses, x minus 8 to the n, all over n squared, 5 to the n power. Another big mess. The n squared isn't here. Root test a little more friendly, or some very clever work. They're all geometric series components, so you could just treat that like a geometric series, but I wanted to have that combination one more time. So I'm going to use a ratio test one more time. 2 to the n plus 2, absolute value x minus 8 to the n plus 1 power, quantity n plus 1 squared, 5 to the n plus 1. That is the absolute value of the n plus first term. I already cleaned up the n plus 1 terms a little bit and got my absolute value where it was still necessary. Divided by a sub n, so times the reciprocal. But still need the absolute value on the x term. Lots of things cancel. Still have an extra 2 left behind. Still have the absolute value x minus 8. Still have the 5. These do not cancel. So I have 2 absolute value x minus 8 times n squared on top. I have 5 times quantity n plus 1 squared on the bottom. Similar to number 3, not just n's in the numerator, not just n's in the denominator, we have them both, and dominant term, n squared over n squared. So same thing like number 4. This times n squared, this is the coefficient that goes with the dominant term at the top. 5n squared would be the dominant term at the bottom. N squareds would cancel, and you're left with that. Or, and this is again the way the book prefers, kick all this stuff out in front. These do not contain n's, so a limit over n, these are coefficients, so it can be kicked out in front. N squared over n plus 1 squared, that limit goes to 1, and all this still pushes along. All this times 1 gives you this. This again has to be less than 1, and once again, we're in case number 3. Now, little things. Now I've got the extra multiplier top and bottom. So what? You want to solve for the absolute value. Divide by 2, multiply by 5. Keep that as a fraction. Make it the decimal, 2.5. That doesn't matter. 5 over 2, right? That's what you would have, so 2.5. There's nothing wrong with decimals here. Negative 2.5 is less than x minus 8 is less than positive 2.5. Still adding 8 to all sides, so negative 6.5 and positive 10.5. Now, again, plenty of people, especially as I go back and plug in, Some people are going to really, really like to prefer to treat these as fractions. So as fractions, that was 5 halves, negative 5 halves plus 8, a positive 5 halves plus 8. 8 would be 16 halves, so negative 11 halves, and this would be 21 halves. No big deal. When I plug these in individually, we'll start with the negative one. So negative 6.5 or negative 11 over 2, whichever you prefer. Oh, I'm sorry. I made a little mistake here. That's negative 5.5. I'm sorry, my fault, right? That would be negative 5.5 here. And of course, now those decimals match like they should. As I plug that in, doesn't matter which way I set it up. Initially it looks a little ugly. 2 to the n plus 1, plug this in. Negative 11 halves minus 16 halves to the n. That becomes negative 25 halves. But now, look at how these things clean up. This is what should happen. This was not a coincidence in number 3. If you have the right endpoints here, as you clean these things up, good things should happen. Negative 25 is negative 5 squared. Negative 5 quantity squared to the n becomes negative 5 to the 2n. Okay? Right here, over 2 to the n. Notice how these things can simplify. You go back and look at the previous one, that wasn't just luck. When you plugged in negative 8, you got a negative 5 to the n over a 5 to the n. These didn't cancel completely, but they could be combined and then simplified. And then when x was 2, you plugged it in, you literally got 5 to the n over 5 to the n. Those are not coincidences. If you did a good job setting everything up, using your ratio or root test correctly, these things should happen. So that here, 2 to the n times 2 divided by 2 to the n, I've got an extra 2. Negative 5 squared to the n over 5 to the n, that becomes a negative 5 squared. Still over n squared. 50 over n squared, p equals 2, which is greater than 1, converges. So I'm going to have to include the negative 11 halves, or the negative 5.5. That's why I went back and showed you with fractions, everybody. If you do that with decimals, that's definitely not so obvious. So it feels fine like you're doing decimals over here, but then when you plug them in, it's like, well, wait, things aren't cleaning up. That's a part of the reason. There's other ways you could make things nice to clean up, but that's like you could break these down to combine it. This is 2 to the n times 2, 2 to the n over 5 to the n can become 2/5 to the n. So there's little other things you could do to manipulate this, but by using the fractions, it became a little bit cleaner to see that canceling. And similar with the other side. If we let x be 21 over 2, 21 over 2 minus 16 over 2 is positive 5 over 2. 21 over 2 minus 16 over 2 is positive 5 over 2. And very similar things happen. 5 to the n over 2 to the n. Up here in this top fraction, these would cancel, leaving you an extra 2. These cancel entirely. 2 over n squared. So in this case, they both converged at both endpoints. Now again, they don't always work out the exact same way the way this did, but both these ended up being p-series. Technically, 2 over n squared is not a p-series. Close enough. I mean, the book would argue you should then do a comparison test. That's close enough, everybody. You would compare to 1 over n squared. Our limit comparison test works like a charm. But these things, I'm trying to show you, these should normally be a little quick last little bit at the end. That's why you confirm at the end. You do this problem and you don't check the endpoints and you feel like, wait, why do I have an open interval and they closed it? Because both of the endpoints worked. So for problem number 4, our interval of convergence -11/2 to 21/2 brackets on both.